welcome back. We're up to part 3 now of our lecture, and we've been taking apart this diagram here that shows the energy balance of the Earth, all the different sources of heat in the form of shortwave radiation and longwave radiation, as well as things like conduction and latent heat transport and so on. And what we found was a little bit surprising. You would think that the Earth would be in energy balance with the solar system around it, and that there would be no net gain of heat, but in fact that's not what happens. We saw, as indicated by that little red box on there, that there was a net absorption of heat by the Earth's surface of about 0.6 watts per square meter. So every square meter of the Earth was absorbing, on average, 0.6 watts, or 0.6 joules per second. That's a lot of energy over the long run, and so we should be trying to pick this apart and figure out why this is. I mean, it's increasing the amount of internal energy on the Earth's surface, which should be causing an increase in temperature, which is consistent with what we learned in lecture module 1. But why? Why is all this happening? It could be any of these terms that are wrong, but we can save ourselves some time here, okay? Needless to say, the science has been done checking to make sure that that energy imbalance is not being caused by an increase in shortwave radiation from the sun, or an increase in, or a decrease in conduction between the Earth's surface and the atmosphere, or something like that. That's all been done. We don't need to investigate all of these possible terms on this diagram here. We can focus on the fact that you and I already know, based on the science, that it's going to be about the greenhouse gases. It's going to be about the absorption and emission of long-wave radiation by clouds and gases in the Earth's atmosphere. These terms that are about how the atmosphere absorbed long-wave radiation that the surface of the Earth was emitting, and then also emitted radiation themselves, some of which back down toward the surface of the Earth. These greenhouse gases that are in the Earth's atmosphere, most notably carbon dioxide, but also methane, nitrous oxides, water vapor, as well as clouds themselves. Clouds aren't exactly a gas, they're made up of little liquid water droplets, but we kind of lump them all together here. They're all good examples of what we call a selective absorber. When something is a selective absorber, that means that how good it is at absorbing a particular type of radiation depends on the wavelength of radiation we're talking about. For example, for carbon dioxide. Carbon dioxide is actually a terrible absorber for shortwave radiation. By and large, shortwave radiation is transmitted through carbon dioxide. Okay? That the light passes through a layer of the atmosphere that has carbon dioxide. On the other hand, in general, carbon dioxide is a very good absorber of long-wave radiation. By and large, the long-wave radiation, like infrared radiation and microwave radiation and so on, that's emitted by things like the surface of the Earth, is generally absorbed by carbon dioxide molecules. There's a good vocabulary word here I want to hit, the word monochromatic. Monochromatic means like with respect to wavelength, or at a particular wavelength, or something like that. Mono, single, chromatic. Chromatic as in color, but remember colors are just different wavelengths of light. So monochromatic means like at a particular wavelength. The monochromatic absorptivity of carbon dioxide might be very low for visible wavelengths of radiation, but it'll be very high for long-wave radiation. Okay? Monochromatic is an important vocabulary word here as we're working on this. Now, these greenhouse gases that are in the Earth's atmosphere they're all trace gases. They're not nitrogen and oxygen, which together make up more than 99% of the Earth's atmosphere. They're little trace gases. The nitrogen and the oxygen in general don't participate in the whole long-wave radiation budget. They aren't absorbing lots of long-wave radiation. For that matter, they're not emitting lots of long-wave radiation. The clouds and the greenhouse gases are the ones that are emitting it. And they're made of matter, that's what they do. They have a very high monochromatic emissivity. They are very efficient at emitting long-wave radiation, and they do so both upward towards space and downward towards the ground. And, well, I'm having a little tablet problem. If we know already, because we're bright little environmental science and atmospheric science and so on majors, we already know that these greenhouse gases are part of the story as to what's going on with the energy budget. A good experiment, little thought experiment we could do is to say how it would be different if the greenhouse gases weren't doing this. What if the Earth's atmosphere either didn't have greenhouse gases in it, or those gases just didn't do this? Well, it turns out with this information that we have from these slides that NASA provided us with these observations of the fluxes of shortwave and longwave radiation and so on, we can think about this. For example, remember at the surface of the Earth we had an energy budget that looked like this. This slide was taken from earlier in the presentation, where we were trying to figure out at the surface of the Earth the energy budget, and we had a gain of 163 watts per square meter from the shortwave radiation coming down from the sky, and a gain of 340 watts per square meter of longwave radiation that was coming down from the sky. And we had losses of radiation, like for example, there was almost 400 watts per square meter being emitted by the surface. We had these relatively small fluxes of heat associated with conduction and latent heat release and so on. And we had, when you added up all these different terms of this heat balance, you found out that it didn't quite come to zero. It came to 0.6 watts per square meter, meaning that the surface of the Earth was gaining heat at a rate of 0.6 watts per square meter. Okay. So, thinking again about the way we did this at the very beginning of this lecture, we can partition this into two terms. There's an energy in to the surface of the Earth term, and there's an energy out. The first term is what the surface is gaining, both in the form of long-wave radiation and short-wave radiation. Once it's absorbed, it's just heat. It doesn't matter where it came from. And energy out, ways that the surface is losing heat, both in the form of like long-wave radiation and in terms of like conducting heat into the atmosphere and so on. All right. So let's do our little thought experiment. What if greenhouse gases didn't do this, or the atmosphere of the Earth didn't have greenhouse gases? All right, so that's not going to affect that first term when I have the white arrow by it there. That's solar radiation coming in from the sky. That wouldn't directly change. I mean, obviously, we're just doing a little thought experiment here. If we really were going to change the greenhouse gases in the Earth's atmosphere, cloud cover would change, the albedo would change, but let's not worry about that. Let's just say same amount of energy in from shortwave radiation from the sun. But that second term, which is labeled in yellow, which is the long-wave radiation being emitted by the greenhouse gases in the Earth's atmosphere coming down to the ground, that would go to zero. If the greenhouse gases either weren't there or didn't do this anymore, that's the term we're messing with. All right? Well, how does that change the other term then? Okay, let's leave the term I have labeled there in white and the term I have labeled there in yellow alone. Okay, those are conduction and latent heat transfer by evaporation. Again, in the real world they would change, but let's just leave them alone as our little thought experiment here. This other term that's almost 400 watts per square meter, that's the long-wave radiation emitted by the surface of the Earth. The amount of that radiation is determined by the temperature of the Earth. That's Stefan Boltzmann's law, right? That is how we determine the amount of radiation something is giving off based on its temperature. And this is a term that's going to change as we change the energy in term. Because as we change energy in, we still need to keep this same balance. And in order to keep the same balance where these two terms still add up to 0.6 watts per square meter, if we've changed one of the energy in terms, we're going to have to change one of the energy out terms. And this is the one that will change. So if we actually play around here with the little math here, and in this white box I've done that there. So instead of it being 163 plus 340, it's now 163 plus 0, because 0 is now the amount of long-wave radiation coming down from the sky after being emitted by the greenhouse gases. To make this thing still balance out, I'm going to have to change that 398 watt per square meter term to 57.9 watts per square meter. That's the only way to make the math still work out. So apparently, if we didn't have greenhouse gases in the Earth's atmosphere and everything else stayed the same, the surface of the Earth would no longer be emitting 398 watts per square meter. It would be emitting roughly 58 watts per square meter. All right, that would be the new rate at which the surface of the Earth would have to emit long-wave radiation. But that is determined by the temperature of the Earth. So if we know the amount of radiation the Earth would have to be emitting, we now can use Stefan Boltzmann's law and just solve back for the temperature. At that number, you plug that into Stefan Boltzmann's law to solve backward for temperature, and you get a temperature of 178.8 Kelvin, which might not mean anything to you because Kelvin's not so easy to think about. Just to convert that for you, that's a temperature of negative 94 Celsius or negative 138 degrees Fahrenheit. Whoa! The planet would be way colder if we didn't have the greenhouse gases, or the greenhouse gases didn't do what they do, namely emit long-wave radiation back down towards the surface of the Earth. Okay, so we can see already that the greenhouse gases are really what's driving this temperature. I mean, all these other terms can matter too, but the greenhouse gas concentration and what those greenhouse gases are doing is really fundamental to determining what the temperature of the Earth is going to be. And the temperature of the Earth is in this balmy region that we have full of life because of those greenhouse gases. These greenhouse gases that are naturally part of the Earth's atmosphere, carbon dioxide, water vapor, methane to a lesser extent, and so on, are constantly in this business of emitting and absorbing long-wave radiation, and that process keeps the surface of the Earth much warmer than it would ordinarily have been if it didn't. Which we could know by thinking about the moon. The moon doesn't have a meaningful atmosphere. It's at the same distance from the sun as the Earth is. And while it's true that during the day the surface of the sun, the moon gets quite hot, and during the night it gets quite cold, averaged over day and night, it gets really, really cold. It's roughly negative 130 degrees Fahrenheit. So we know that actually the Earth is kind of too far from the sun to support life without the greenhouse effect. We are entirely dependent on making this work. Okay. Well, but of course, you know as well as I do that we're going to be able to show that we've also messed this up. But we'll get to there over the course of this module. Before we move on to part 4 of this lecture, though, let's do a couple quick questions here. Question 7. For the radiation balance of the Earth's atmosphere system, greenhouse gases directly affect A, the long-wave radiation coming down from the sky, B, the short-wave radiation coming up from the ground, coming down from the sky, C, the long-wave radiation going up, short-wave radiation going up, or D, the albedo of the system. Now, realistically, if we change the amount of greenhouse gases in the Earth's atmosphere, all these things are probably going to change as we change cloud cover and things like that. But which one is the one that is actually directly caused by the greenhouse gas concentration? Make a choice from those 4 options and get a little feedback before you move on to question 8.